Hello, so this is my presentation on fluorescence resonance energy transfer, also known as FRET or FRET for short. My name is Alexandra, and the goal of this assignment is to learn about the principle and application of modern techniques used in cell biology. So, to start off with some background information and the actual application of FRET, what is it? It's basically a distance dependent physical process by which energy is transferred non-radiatively from an excited molecular fluorophore to another fluorophore. This happens via two processes: intermolecular long-range dipole and dipole coupling. This is a tool used for determining the distance between two fluorophores, and it is a non-radiative transfer of energy. And just to talk about the application in general, you have to choose the right fluorophore pair. That is essential. If you're not choosing the right pair, you might have some complications down the road. You have to make sure that you have a suitable pair of donor and acceptor molecules. And also, just to touch base on some quantification techniques, you want to make sure that you're changing that there's change in the fluorescence emission intensity of the donor, sensitized steady state fluorescence emission intensity of the acceptor, decrease in the donor lifetime, and change of fluorescence polarization. Furthermore, I just want to touch base on these bullet points here. FRET is a highly distance sensitive measurement that is compatible with protein studies. So this is essential with proteins. You want to make sure that you're choosing the right fluorophores, as I mentioned. You want to also be aware of potential pitfalls and practical considerations. Also know that there's a wide variety of FRET quantification. It's not kind of like a one size fits all. There's a wide variety. You just want to make sure that you're using the right technique for the right experiment. Now going on to this primary research study. So in this study, the researchers reviewed the current stage of FRET methods development with the main focus on its application in protein studies in biological systems. The key question being asked here is, does altering the donor-acceptor ratio affect FRET efficiency? So the image here demonstrates SpectraFRET, which is a single HEC 293 cell co-transfected with chloride channel subunits, and it's also shown with CFP. The figure was divided into three regions depending on the donor to acceptor ratio. Only at the high donor to acceptor ratios the apparent FRET efficiently approaches the true FRET efficiency. So that's the question being answered. In an ideal experiment, it's known that the emission properties of fluorescence should not be affected by the interaction between the fluorescently labeled molecules. However, this study and this research showed that was not to be true. Hybridization of an unlabeled strand of polynucleic acids has shown to also mess up or intervene with the chlorophyll on a labeled complementary strand. So now moving on to the question that was asked for this presentation is, if I were a scientist working on ACE2 or spike protein of SARS-CoV-2, what questions would I ask and why? So if I were a scientist, I would definitely ask, what specific protein is being attacked? Has that protein been identified? Have the mutations been looked at? And how many proteins are being affected? Is it a lot? Is it a little bit? And just kind of go off of those questions. So my proposed hypothesis is, does the more proteins being attacked have an effect on how fast COVID will spread through the immune and respiratory system? So as we know, different patients are having different levels of COVID. Some are being intubated in the hospital, some don't even show symptoms, some don't even have a headache, and others will have skyrocket fevers. So that was kind of my experiment that I wanted to do. So for this experiment, I would want to use the use of FRET spectroscopy and specific protein analysis. Why? I would want to know I would want to identify the proteins being affected. I would also want to visualize the mutations. I would want to separate those affected proteins and count the proteins. By counting the proteins and also looking at how the patient is doing or how the respiratory and immune system is doing, I would kind of have an idea of how fast it's spreading. And by knowing how many proteins are being affected, you can kind of see if COVID is being spread fast or if it's being slow. Or perhaps there's not even a change. Maybe it has nothing to do with the amount of proteins being affected. So I would kind of do that. And I believe that the more proteins being affected is the faster the rate and spread of COVID in the immune and respiratory system will be. I believe that if you have a sick patient, maybe 68 years old, 70 years old, and he has more proteins being affected, and you're able to identify those proteins, you can see the effect and the rate of COVID being spread through the immune system and the respiratory system. So that is it for my presentation, and this is my citations. Hope you enjoyed.